Hello everyone, my name is Shrishti Hiramat and today I'll be presenting the topic of matrices. Let's all together explore their history, fundamentals, operations and applications. Well, matrices are simple structures that power complex calculations across various fields. Moving on to the history of matrices, matrices have ancient roots. Chinese mathematicians used them to solve system of linear equations and early civilizations applied them in accounting and surveying. In the 19th century, Arthur Cayley formalized matrices, leading to the modern development of linear algebra. While he also introduced matrices as mathematical objects and developed the Cayley-Hamilton theorem, his contributions laid the foundation for advancements in data science, physics, and computer science. And a brief overview about him. He was born on August 16, 1821 in Richmond, England. And his key contributions are introduced matrices as mathematical objects and developed the Cayley-Hamilton theorem. Fields of his study in linear algebra, algebraic geometry, and group theory, while projective geometry as well. And his notable achievements are defined matrices for solving linear equations and transformations, developed Cayley tables in group theory, published nearly 1,000 papers in pure mathematics. His legacy was a founder of modern algebra. His work underpins advancements in data science, physics, and a computer. He died on January 26, 1895 in Cambridge, England. Moving on to the introduction of matrices. Matrices are rectangular arrays of numbers arranged in rows and columns. They represent system of equations, transformations, and relationship between variables. In linear algebra, matrices are fundamental for modeling systems, solving equations, and understand the complex relationships. While moving on to the fundamental operations of matrices, matrices support several basic operations. To name few of them, addition, subtraction, multiplication, and scalar multiplication. While addition is the adding matrices involves combining corresponding elements, and subtraction in matrices involves subtracting corresponding elements. Matrix multiplication involves multiplying rows of the first matrix by columns of the second matrix. And the last, scalar multiplication, is multiplying a matrix by a scalar involves multiplying each element by the scalar. There are several forms of matrices, and to name them, row matrix, column matrix, rectangular matrix, square matrix, zero matrix, diagonal matrix, scalar matrix, unit matrix, and upper and lower triangular matrix. While the square matrix are matrices with equal rows and columns, identity matrix, square matrices with ones on the diagonal and zeros elsewhere, whereas the diagonal matrix, square matrices with non-zero elements only on a diagonal, whereas the zero matrix, matrices with all the elements equals to zero. And moving on to the inverse matrices, the inverse of a matrix A is another matrix denoted by A to the power of -1, which is A inverse, such that when multiplied by the original matrix A, the result will be the identity matrix I, and it is expressed as in terms of equation, where A is the square matrix, same number of rows and columns, and I is the identity matrix which has ones on the diagonal and zeros elsewhere. And to find the inverse of the matrix involves using Gaussian elimination or other techniques to solve a system of equations. For that, we need to first calculate the determinant of A and find the cofactor of A, take the transpose, and then multiply the determinant. And its applications are inverses are used to solve linear equations, transformers data, economics and game theory, 3D graphics and animations, and to analyze systems. And this one is the example for the inverse matrix. To start with the original, let's consider 2 into 2 matrix. Calculating the determinant here, if A is equals to ABCD, then A inverse is equals to 1 by AD minus BC, and the transpose of the A is D minus B minus C and A. So A is the inverse of A, and the 1 divided by is the determinant of A and adjoint of A. And to note that A inverse exists only when AD minus BC is not equals to 0. There are several usage of matrices in real world. While the applications are they are in network analysis, machine learning, computer graphics, and many more. Whereas the network analysis or matrix represent relationship and connections in networks. There are graph theories and routing algorithms, and machine learning and data science have the vital role. Data representation and principal component analysis, that is PCA. Having said that, there are several applications. It is in computer science and data science, graphics and animation, optimization, cryptography, quantum mechanics. In computer science and data science, processes the large data sets of machine learning algorithms and performs dimensionally reduction, that is PCA, and image compression. While in the graphics and the animation, used in computer graphics to manipulate image and render 3D models, essential for virtual reality, that is VR, and augmented reality, that is AR. Optimization matrices are used to optimize process and find the most efficient solutions. While in the cryptography, it is an encryption and a decryption. Its classical encryption methods involves Hill crypto. Matrices are used to encode and decode messages, are also used in more advanced cryptographic algorithms for securing digital communication. While in the mechanics, matrices are used to describe quantum states and operations in the quantum mechanics. And the future scope of the future scope of matrices lies in the advancing technologies like artificial intelligence, quantum computing, and big data. Enhanced algorithms in AI rely on matrices for neural networks and data representation. In quantum computing, matrices describe quantum states and processes. In big data, they enable efficient analysis of massive data sets. And moving on to the conclusion, the last part of the presentation. In conclusion, matrices are fundamental tools in mathematics, simplifying complex data and systems. They solve problems in linear equations, transformations, and data analysis. From theoretical studies to practical applications in science and technology, matrices are essential for modern advancements. Thank you for watching. I hope this presentation was provided a valuable insights into the world of matrices.